Great.
One last question.
Yeah.
Thank you. One last question for the test. I think so. Right, that was working. So we have this train test in the bottom row, and do we need to know how the data between train and test was split by the original model, or
because the original model only have the train data set. Testing data sets you decide yourself for experiments purposes.
And if it's completely black box, how can we train? Like, do we assume that we have the source code of the actual network so that we can train it?
Yeah, you can assume that. You can assume that. Let's say you can assume you know the target model is less than 50, and then your shadow model can also be less than 50. You can assume all the hyperparameters be the same. But actually, empirically, so this is ResNet, this is VGG, also works.
So you just take a similar model, not necessarily the same you take a model for the same problem.
Yeah.
Thanks.
Yeah.
So we should have an assumption for the training data set as well.
Okay.
Should we have an assumption of the data set as well?
Right. You mean normally we assume these are from the same distribution. Yeah. But later we'll talk about what this same distribution means. But normally in practice, you have a data set, you split by 4 parts. The first part used to train the target model. The second part and third part is training testing for shadow model. The leftover part is testing sample for target models. When you do experiments on paper. All right, so the whole pipeline of this thing, I mean, not only machine inference. So if you are doing something else, let's say you are doing, let's say, attribute inference, or you are even sometimes background detection, you also have heard the notion of shadow model. Some people call it the surrogate models. The whole thing of this is because we don't have enough information on target models, I have to build myself own things, and then I'm using to simulate the situation to get data to train my target model. Yeah. Remember, I mentioned machine inference is a sample level attack. For sample level attack, normally one shadow model is enough. But however, if your attack, let's say, is a model level attack, I want to know, for example, let's say how many samples are used to train a certain model. In that case, you also need shadow model, but your shadow model need to be many, each of them with different size, to simulate the situation. So this is like a macro level and macro level. Yeah. And another thing for this pipeline is, let's say, the attack model is a machine learning model. So basically, you are using a machine learning model to attack machine learning model. But the target model here is only, let's say, a testing sample for this attack model, which means this one is on a higher level for the attack model. Attack model is on a higher level. So it's it can be applied. I mean, for this image, actually, it's only a sample. You can put other images. The attack model will also carry this member. All right, so one of the major assumptions of this attack, as you just asked, is to assume that the attacker has a data set coming from same distribution as the target model. So, however, so let's say if you want an attack model built by Google or Meta, so you need to assume the attacker has the same level data set as that, which is too tough. So back in 2019, that time we say, how do we relax this assumption? So back in 2019, our idea was like you just try a different data set, just a different data set. This different data set can even be, let's say, different modalities. So this can be image, this can be text. This can be NLP, this can be image data set. Then all the other things are the same. Okay? The reason this can work, is because my attack model's input is not the image or text itself, it's the posteriors. Yeah, it's the posteriors. So the posterior as the input, the attack model still work in some sense, in certain cases. For example, machine inference, as I said, is a boundary classification. A sample can be member or non-member. On this slide, I have 2 heat maps. On the left is the boundary classification precision, the right is recall. Everything on the diagonal is I'm using the same distribution data set to attack the same distribution data set. Everything off the diagonal is why I'm using a different data set. Darker the color, better performance. Using many cases, things off the diagonal also have good performance. For example, I'm using CISPA 100 to attack news data set. Still works. News is NLP, CISPA is an image. The reason this works because the attack model only captures the posterior overfitting behavior. So no matter what model you are, so if you're a member, you are overfitted, normally you have wide confident class. In that sense, yeah. But however, this is not really the final solution because this is only a demonstration. Because you see, on these two heat maps, not everything performs good. It's not like you can use anything, transfer anything. Yeah, many cases they have the light colors, which means the attack performance is not good. So which means that if you one day give me a model, I don't know which shadow model, which shadow data set should I choose to attack the model. I only know that using some things might work, but I don't know which one to choose. So that was 2019. Yeah.
I think there was patterns.
Yeah.
Like doesn't work.
Yes, it doesn't work.
Explanation.
I mean, the question is, let's see, there's an adult data set that doesn't work at all. I mean, the explanation is failed. It's not like, I mean, this one you cannot guarantee it always works. It's only possible that some of them can be transferred to attack, but not always that I can really use any data set to attack any data set. The reason it doesn't work probably is a shadow model, target model, or big network very different. Yeah. Right?
Sorry,
Yeah.
Hello. So can you go to the precision uniform?
Yes. Before I solve the problem. Yes.
So I can see that for CISPA 10 and for the news, we got 0.92 precision.
Yeah.
So what is the probability that you will get the same with both? For example, if we repeat the same experiments.
What do we do? What?
If we repeat the same experiments, if we do it like again, so is it what will be the probability that we will get 0.92 for this?
What is the property?
Probability.
I think this all these experiments are repeated 5 times. Yeah. It's not like a single time shot.
Okay.
All right. So that was our idea back in 2019 in terms of, let's say, you can use a different data set, but as I said, it's only a demonstration. We don't know if you want to really do that, like which data set you use. But back in 2021, we realized that the problem is not that complicated. All you need to do for the shadow data set, you don't need to be dramatically use a different modality data set. All you need to do is just open Google and download images. For example, if a target model is cat panda dog classifier, just open Google and download enough number of cat images, dog images, and panda images. I download from internet, I train the shadow model, everything stays the same, attack still works. Performance is not that bad compared to the same distribution data set. Very similar actually. The reason, I mean, this attack, the good thing about this attack is that this is a, now when you face a classifier, as long as you can get images or whatever sample from the internet, you can do the attack without being just trying for luck. Yeah. So reason this happens, why this works, is because the notion of same distribution data set in the context of attacking machine learning models is not well defined. So right now, what is considered a same distribution data set? I'm not talking about the OD in the machine learning community. I'm only talking about, let's say, the attacks against machine learning models, the same distributed data set. So this notion basically, I mean, right now people assume as long as I have a data set as split by half, this two-part data set all coming from the data set called ImageNet or called SafeBar, I consider them as the same distributed data set. Yes.
Sorry, to make it certain, it's enough to train one shadow model.
Yes, it's enough.
How do we know that actually? I mean, it works, but do we mathematically know it that it's sufficient somehow?
This is empirical, not mathematical. So
Okay.
first membership inference attack, authors said indeed we train multiple shadow models. But 2019 we only trained one. And since that, everything doing membership inference with shadow model only train one. Multiple doesn't help much.
Okay.
Yeah. How do I explain? If I'm using, let's say, if I'm using a different modality data set, yeah. So for this, because I didn't mention some details. So for example, the attack input, I only take the top 3. Yeah, so it can be 10 classes, it can be 100 classes, only be top 3. So this is not unified there, but you can do something further smarter to like the justice. Yeah. All right, where was I? Yes, okay, so the notion of same distribution data set in the sense of a technical machine learning model is not well defined. As I said, so right now, so at least the researchers consider data set from same distribution. What they do is I have a data set, they call CISPA. I cut it by half. Because these 2 halves are both from CISPA, I consider them as the same distribution. But the thing about this data set originally, how they were created, it's definitely not the students from CISPA, this institute, have a same camera and same set of photographers taking photos at the same time. Instead, I mean, for example, CISPA is from Flickr. It's also collected from the internet. And then all they do is just do some, manual checking, manual labeling, etc. So which means that if you download from internet, as long as same class, at least for that access, should work, which also works. But of course, it also has a constraint. That is, if you are targeting, I mean, if you are attacking some target model that's with very specific samples, like some very high advanced medical images, which you cannot easily download from internet, it doesn't work. Yeah, but I mean, for normal cases, normal samples, as long as you can find samples on internet, it should work. Yeah. More questions?
Thank you.
Awesome. More questions you ask, less I can talk.
Thanks. This attack model only takes as the input 3 real numbers.
Yes.
So is this model explainable? Because the input space is super small, right? It could be visualized.
You're right, but the problem itself is not that hard. I'm only deciding whether a sample is member or not. I mean, is a member or not. And then once the so-called overfitting level, normally you have 1 or 2 classes with very high confidence.
And are these attack models explainable, or if you look to how this model to this model function?
We haven't seen any explainability analysis on the attack models, but I can guess that normally if you want to judge whether sample is a member, you check on the highest class. Normally. But we didn't do that. Okay. Because your question will be linked to the next attack, which is yes.
Could the attack model be replaced by a simple K-Elgar divergence against the classes per class there?
Excellent question. Wait for 10 seconds.
Yes. Because it feels like it could. Yeah.
Yes. Back in 2019, I also think it could, but at that time, the PhD students I'm working with, they insist not like to try this much, but actually it's in the end, I'm expecting to try it a bit. So third attack nowadays is called metric-based attack. All you need to do is for third attack, you don't have the shadow data set shadow model anymore. So you have the sample, you throw it inside target model, you have the posteriors. From the posterior, for example, that time the student only want to try, let's say, highest posterior. They set up a threshold, let's say 70, for example, 80 higher than 70. Okay, you are a member. Yeah, because it's simply using the the overfitting behavior model. Of course, as I think that we also tried, let's say you can calculate the Shannon entropy. Your entropy is lower.
Yes.
Yeah, so you are a member.
Yeah.
And then that time, I think that's it. And then back in 2021, so 2 people from Princeton wrap this whole thing up with more fancier, easy to compute metrics to build a class of attacks, so-called metric-based attack. So which means in 2023, so if you want to do memory inference, you want to do it quickly, you can just try metric-based attack because normally the performance is similar to the shadow-based or shadow model-based attack.
Yeah, that makes sense. Thank you.
Yeah, of course. This is why you need to choose a threshold. Because if you wrap this whole posterior information into one value, you need to see this value bigger or lower than a certain thing and decide it's a member. But the truth threshold, I think the mainstream thing is still you need to train a shadow model to find a threshold. But I mean, if you want to experiment wise, if you want, let's say, use some, you can use some metrics that's not sensitive to any threshold, like AUC area and the RC curve or precision recall curve works. Yeah.
So if I did it right, this attack basically picks up a threshold on the probability of classification value, and then
Yeah.
decides based on that if it's a member or not. So,
Yes.
but to train it, we also need some sort of shadow model. Do I get it right or not?
So what?
To train, like, for example, some model that will guess this actual threshold, we also need a
Yes,
shadow
that's
model.
what I just said, yes.
Okay,
Yes.
I need to run this time. Okay.
Yes, so you need you need still shadow model to get the threshold.
Okay.
But I mean, eventually don't be too constrained about the threshold, because the thing is threshold in the end is always, even you have a classifier also has a threshold. Now binary classification threshold is 0.5. But depends on scenario. So let's say if you really want to attack that, you really want to get a single sample is a member or not. I mean, 0.5 is also not that good threshold. So you always need to adjust it depending on the case. Yeah.
Okay.
All right. So basically, that's the membership inference in a nutshell. So right now, I think there are quite a lot of papers, 200, 300, 400, 500 papers on membership inference past few years. So we are the second, not the first. But I mean, however, most people are still either doing metric-based attack or shadow model-based attack. So this attack has been studied well. And actually, another major thing that people do nowadays, because in our paper, we take the largest three posteriors, we rank it from high to low, so it needs. And then, but in many cases, you don't need to rank it, it still works. But this also depends on the model. So recently, I mean, I think 1 year ago, recently it's 1 year ago, our lab will try that if you do a membership inference on, let's say, a many class classification, like 1,000 class classification, you throw directly to 1,000 posterior inside, doesn't work well. However, so those cases, you still better take top 10 or top 3. Works better. So it really depends on the model. So all I said here is some general framework or general principles, but if in practice you want to do membership inference, so many things you need to be considered. Many things, if you tweak a simple parameters, the result will be very different. Yeah. Oh, right. Right. So membership inference, so far everything is assumed the target model give you the posteriors. But what if the target model only give you a label? Which is very common, let's say, if you are using machine learning models. It will not tell you this is a competent panda, but it will tell you this is a panda. Yeah? So we don't know whether it's competent or not anymore. So in that sense, can we do membership inference? So for a few months or 10 months or something, I thought it's not possible until I have my PhD students figure out 2 ways to do it. So it's so-called label-only membership inference. So in our concurrent work, people from Google actually also published a label-only membership inference. By the time that the 2 papers appear archived is only 3 days apart. So in our paper, we did 2 attacks for label-only case. Remember here, the label-only case, the target model only gave me the posterior. Okay, only give me the posterior. Sorry, only give me the label, not posterior. So our first attack is called transfer-based attack. So I have an attacker here, and then assume the attacker has a shadow data set, a local data set from the same distribution and target model data set. But this data set, I neglect all its label. Yeah, I neglect all its label. And then I'm using each sample in this shadow data set to query the target model. Each sample I query to the target model, I get a label, right? Because target model only give me labels, not posteriors. So after the process, I'm using target model as a labeling machine. Yeah, it basically put label on my non-labeled data set. Once I have this, I do a very familiar thing that to get a more familiar now. So I have the data set, I split the training testing, I'm using training to train a shadow model that is similar to target model, so shadow of target model. Once I this, I throw them all inside to get posteriors. Why I can get posteriors? Because shadow model is designed by me. Yeah, so I don't need to constrain, they only give me labels. Once I have this, I'm using this data set to train that target model. Once that target model is trained, my target model input is posteriors, not label, posteriors. Once my target model is trained, to do the final attack, I still want to know this one is part of this. Yeah, this image is a part of this green target model. I throw the image to the shadow model. Shadow model give me posteriors because shadow model is controlled by me. And then I throw the posterior inside, tell me it's a member or not. Know that this image is never a member of the shadow model. Yeah. Okay. The reason this works lies in here. That is the so-called labeling process. If my labeling is good enough, my data set have we will learn enough information from target model. So which means once I'm using the data set to train the shadow model will be very similar to the target model. So which means that if these two models are similar, extreme case they are identical, which is not possible, but let's say the upper bound they are identical. So if the target model think I'm a member of this, then I'm a member of this. Yeah, that's a so-called process, the whole process of this transfer-based attack. I assume question. Yes.
It only works when your model is well fit. It does not work if your model performs 80%, right?
That's the problem for all membership inference. Not only this specific to this attack. I will talk about that later.
Yes.
Here we have the data set with script labels. Couldn't we just so we take the training data set and strip labels and pass it through the target model? Couldn't we just do it from with the data from the start?
Yes, but in that sense, we tried the experiment, it's not that good because you don't have the connection with target model anymore. So you will lose some information from target model, which means this one will be less similar to this. This one will be less similar to this. Okay. Yes. All right, so this is the first attack. The second attack is the more popular one, and also the one that Google did. It's perturbation-based attack. So you guys heard about the three examples, I think. Yeah. Or normally many people like to call it a virtual attack, which in English makes no sense, this term. Yeah. Anyway, so adverse examples. So basically, when talking about adverse example, it says the most popular security attack against machine models. It works as the following. So if I have an image, I start to target model, tell me a panda, and then the attacker adds some human imperceptible noise on the image, specifically optimize the craft, add to this image, I throw this to target model suddenly recognize me as a cat. Yeah, this two images looks identical, but however, it's still some noise difference. Even though it's not on this slide, because these two images are the same. Yeah. But however, that's the general notion of adverse examples. Also, it's the most popular attack. I mean, probably 3,000 people has worked on this for the past 10 years. Yeah, till today, I guess. Until today. So we create many new research directions, and government or whatever funding agency put a ton of money on this. Anyway, so why I'm talking about this? Because it turns out that we could leverage a property of adverse examples to do membership inference in label only sense. The basic assumption is, I mean, the intuition is like the following. If it's a member sample, it's harder to make it to an adversary example. The harder is quantified by the magnitude of the noise. Yeah. So for a member sample, you need to add a larger noise to make it misclassified. For a non-member sample, less noise. You can use the magnitude of the noise to judge whether this is a member or not. Again, metric-based, you find a threshold. Yeah, you can find a threshold with shadow models, whatever things. But however, the intuition is that a member sample is harder to become an adverse example than non-member sample. Yeah. Questions? Yeah.
So for some reason, also it's supposed to be the opposite. It's like if model overfits in something that we could change a bit, then I don't know, it's something from the background that doesn't matter for like completely new images.
No, if you're a member sample, the model remembers it really well. It remembers it really well. Yeah, so it's also very overconfident. I mean, it's overfitted on one class, very confident. So you can do other examples to reduce that class. For another high confidence class, we need to add more noise. That's the intuition. Yeah. Yeah.
Usually to perform these perturbation-based attacks, you need access to the gradient, right?
No. This, I mean, technically yes, but this is a black box. So we are using this black box way for doing other examples, like hot pit jump. There are also specific method for this. We didn't invent anything, but just borrow the literature from the other examples. If you do, yes, if this is white box, you can do, let's say, really based optimization is faster, I guess. Yes.
Yeah, if you're doing it white box, what is then better? Like the previous one where you do it on the like the posterior, or this where you do it?
We haven't tried, but I think posterior is better. It's more straightforward. Yeah, so this signal is more, I mean, the overfitting level high confidence class is more linked to the problem itself. Yeah. This one is not like 100% of member sample ratio, sure. It's not 100% fully matched. Yeah. I'm definitely the winner of the most question lecture of this.
I think it's easier to do it if you have a whiteboard access, because you can do something similar to backpropagation, but not trying to fit to the labels, but what you actually try is to fit to the as much difference as possible. So you kind of change the objective function in a sense. So you kind of optimize in a different direction. That's why it's simpler when you have whiteboard access. But if you don't have, then you change the input, and that's all you can do.
Yeah. Which means that it's a sample. I mean, we'll talk about the next slide. So one of the major things, so back in this paper was published in 2021, so we did it in 2020, I think. And in 2021, my group will publish, we submit other papers to this top tier security conference, so-called top tier security conferences. So many of our attacks are also other kinds of machine learning model, but are posterior based. So the model gives us posteriors. In many cases, the reviewer tell us, actually I remember at least 3 times, the reviewer tell us, why not you compare with the state of the art, the label only membership inference. So first of all, label only and posterior based, they are not really comparable, because label only is not the state of the art. It's only a different threat model. Posterior give you the full posterior, label only give you the label. Yeah. And another thing is, in some cases, yes, label only performance is better, a little bit better than posterior based attack. But however, to do a successful label only membership inference in the example sense, one sample add different noise, said black box and other examples, add different noise. You need to query the model with different type noise around 2,500 times to get a good performance. For posterior based attack, one image, you only need to query the target model once. It's 1 versus 2,500. From the defender point of view, practical defender point of view, so you can easily spot that I have my model if I'm getting an image with very similar but not the same thing for 1,000 times query. So this one, if you guys still want to work on label only membership inference, we'll try to see how do we reduce this. To make less number of queries, you can still do a label only membership inference. I didn't follow the literature that much, but label only membership inference is an interesting paper that we got the static while, but I'm not aware of any new advancements. So it seems that we did this, people know this, and people decide, but no one keep on pushing for this. In my lab, I normally don't actually find the topic and keep on doing several iterations. So yes, if you guys like to, yes.
I have a question regarding the metric that you use. For example, here is area under the curve. Previously was recall and precision, but like more established metric, like recently by the Carolini was TPR at FPR 1%. So why not using this here?
Yeah, because I'm not from the future. For is 2020. That have this membership from the fourth principle is not there yet. Okay. Yeah. Although that paper is, let's say, from low recall, high precision. Yeah, that's what it's going to be. It's still, it depends on your scenarios. Let's say if your membership inference, you want to have a whole data set. If I want to get as many members as possible, low recall, high precision might not be the case. It depends on the case. Yeah. Yes. Yeah. But the membership from the first principle, I think that attack should be better than the ones I talked about. But however, that one is too expensive. To guess one member, you need to train, 1,000 or 10,000 models, half of them with the member sample, half of them without the sample.
It's a couple of dozen.
Yeah. depends on what kind of model as well. Yeah. So that why is the major thing on this. Right. Don't be very fast. Anyway, so memory inference has been studied for, let's say, 5 years at least. So, I mean, many, as I said, many papers have been working on this. But however, this one is not as successful as reduced examples. Reduced example, normally nowadays you can guarantee normally any model I can do reduced examples. Memory inference still works if your model are somehow overfitted. Yeah, if you have a perfectly not overfitted model, or even your training testing accuracy is very small, memory inference in that case does not work, which make it harder for being deployed in practice. Okay, I mean most of the models I know in this domain are on, let's say, this academia style models. Like the largest, I mean, there are only a few papers try the ImageNet. But the ImageNet is also not the largest data set because you can use line or whatever thing. The model is actually large language models. Yes, what they work. Yeah, but those models normally, especially if your model is trained with really so many data samples, memory inference signal is very weak. If someday, hopefully some of you guys, if come up with a new attack model or a method that really can guess, let's say, a ChatGPT style memory inference, yeah, so I mean, it will be a really huge advancement in this field. But right now in academia, it's a very popular topic. People know it works, but however, the current model has to be overfitted. If it's not, doesn't work. Yeah. More questions? Yes.
It's a comment rather than a question. We have been doing some research on membership inference for large diffusion models.
Yes.
Like mainly stable diffusion.
Yeah.
And this was exactly the case that attack methods that work perfectly but present on like Cypher-10, Cypher-100 even diffusion models.
Yeah.
They all failed when we tried to do membership inference for stable diffusion, which is trained on billions of images from light. The signal was very weak, and the model was there was a slight difference in the signal, but it was able to generalize so well across the data set.
Yes, exactly. That's why I don't like to work on memory inference anymore. You feel like you work for this for 5 years and then still it does not work on real models.
Yeah. Do you have like some intuition on how to break this limit and make
I hope I know. No, it depends because the thing is, of course, you could also relax your attacker assumption. You go for, let's say, white box attack, which means you have more information, not just the outputs of the model. Even in those cases, I think till today, not many people are find a very smart way to show the white box attack is better than black box, which by definition it should. But however, still not much difference. So I guess you could, I mean, we had a paper in 2021 CCS, where at that time using the training trajectory of the epochs to do the membership inference. It might help a bit, yeah. Or you can use the membership inference from the first principles. For one sample, you train 1,000 of shadow models. It might work. Yeah, but however, for stable diffusion, it can't always. It's impossible.
Yeah, it was a problem that we had.
I mean, spend €1 million for one paper that you are not even sure it got accepted. Not a good deal, I guess. More questions?
Maybe
Yeah.
Do you see like some cheaper alternatives for shadow models that require full training from scratch? Like maybe focusing on. So do you see an alternative for the classic shadow models that are like trained from scratch on a given data set, like a shift towards some other
like monitoring some other kind of behavior which doesn't require full training?
It depends. I think nowadays, if you do machine inference, the entire model is fine-tuned. I mean, it's both for pre-trained, shadow model is also pre-trained, and then you fine-tune with your own data sets. So in that sense, yeah, it should not be that much of a difference, if this is your question. Or you want to say I'm having a cheaper shadow model for other kinds of attacks?
It's like more a general question is with pre-training, there are several, there are some issues with pre-training.
Yeah.
You have to be careful with that.
You mean like once you have a pre-trained model, you fine-tune it, basically the model by default has two data sets. One it has the base trained data set, the other is fine-tuned data set. You want to separate, let's say, which one give you higher influence, etc. You know? I mean, any people study this? You can try. So I don't think people study this. But of course, based on my lab's own experience, at least what my student told me, so normally the fine-tuned data set has a higher influence on the model. So let's say if you want to have a model that is fine-tuned on data set, so the original data sets match the signal on this model is weaker. All right, let's continue to the second attack. Sort of data reconstruction, but in a specific setting called the online learning. So that was again old work, I guess. But I mean, this work yes. So let's explore. So nowadays data is generated all the time. So every millisecond. Even the time we're doing this is generated data because the lecture is being recorded, all your questions being recorded, data is being generated. What this means is that for large companies or strong companies, when they train a very powerful model, maybe in a few days or a few weeks, it got outdated because it does not incorporate the newest data got generated. Yeah. To solve this problem in machine learning setting or industry, to do something called online learning. Online learning nowadays, my model is trained, and then when I have new data coming in, so I'm using this data set to further fine-tune my model a bit. Okay? So that's, I mean, probably the most practical way to improve a model with newest data. Especially now if you enter the large model era like LLM, so I don't think every time you have new data, you train a new LLM from scratch. Otherwise, it would be too expensive, impossible. Yeah? So this is online learning. So we're wondering whether this can constitute a new attack surface against machine models. Suppose the following. So I have a target model today. I throw an image inside. The model tell me, okay, 70% panda, 20% dog, 10% cat. So then the company suddenly collects some new data. I update the model. Tomorrow morning, if I'm using the exactly same image per the model, I will get a different possibility. Right? Because the model got updated in the sense that the weights on the model is changed. Yeah, no matter how significant or not. But however, I mean, they change a bit, normally the posteriors will be different. Yeah. So whether this is a new attack, because the thing is, I have two same image prior to the model with different versions. I get different posteriors. And these posteriors, the difference, all because the data set used to update the model. So this paper, our question is, let's see, from this posterior difference, can you reverse back the information of the data set used to update your model? Yeah, because your updating set is the reason that the cause change of the posteriors. Then whether we can reverse it back. It's sort of like a reverse engineering. Yeah. That was a 2020 USENIX paper. So for this, we build a general so-called attack pipeline. So we have a target model. And then the attacker, of course, not using one image to carry the model data version. I'm using a set of images. I call it a probing set. Yeah, this set, say 100 images. Okay. I'm using this 100 image first to carry one version of the target model. I get 100 posteriors. Okay. And then attacker, the model owner update the model. Then the attacker use the same probing set with the same sequence to carry the target model. I get another, let's say, 100 posteriors. Okay. Each class is three. Each prediction gave me three numbers. 100, so 3 times 100. So I have 300 dimensional vector. I have two 300 dimensional vectors. I do simply a subtraction of these two vectors, I will got another 300 dimension vector. Yeah, I'm just using the first one minus the second one, the upper one minus the lower one. And then we build something called the encoder and decoder. So the encoder is, let's say, I put the posterior difference into the encoder, and then the decoder, I mean, for this work, we did actually 4 attacks. So for different attacks, we are using different decoders. So the 4 attacks, the first 2 assume, I mean, it's only a demonstration, so it's not realistic assumption. We assume entire model is only updated with 1 image. Yeah. And the second, the third and fourth attack, we assume entire model is updated with a set of images. Okay. And I don't know what exactly slides I have, so let's see what attack we'll talk about. So I have 4 attacks. So no matter what attacks, our encoder part is simple. So this is the 300 dimension posterior difference. I throw it to encoder, which is simply a multi-layer perception. You can build whatever number of layers, like 2 layers, 3 layers, 4 layers, right? And then you can reduce this dimension to, let's say, 100 or 128 dimension. And then I throw it to the decoder. Okay? Before I talk about the architecture of the decoder, I will also talk about how to train your whole model. Yeah. Again, we leverage on somehow innovative, but we leverage on shadow model. So I have a target model, then I build a shadow model. Once I have a shadow model, I simulate, let's say, n different updating sets. Okay? Because I also have some local data set that's not used to train this, but I'm saving it to update model. So each of the model I update in shadow model, yeah, and then I will get n shadow updated model of the shadow model. Yeah, we do it in parallel, yeah, not sequential, yeah, parallel. Yeah. So once I have this, I'm using the same probing set from my final attack, because I mean this one is decided by the attacker, so I'm using the same probing set. I'm using it to probe the original shadow model from the first shadow updated model. I will get the first posterior difference. I call it shadow posterior difference first. Yeah? And then I'm using it to probing the the other things I got other in total n posterior differences. Yeah. Probing that I only need to probe the entire shadow model once. And for this I probe them each. Okay. And then I will have n posterior differences. Once I'm having this posterior difference from 1 to n will be the x of my attack model, to train my attack model, which means become the x part of training the attack model. And then this information in the shadow updating set will be the ground truth, depends on what attack you are doing. Okay, so if your attack is doing is reconstruct it, so I'm using the whole thing of this. If I'm just guessing the label of them, I'm extracting the label out as my ground truth. Okay, so that's the whole process for training this attack model. So I think that yes, first slide we talk about 2 attacks. First attack is a simple setting, unrealistic setting. We assume the target model is only updated with 1 sample. Yeah, unrealistic, but I mean we can see whether it works. So if and then my goal is to reconstruct this single image that got used to update the model. Okay, so we do something following. So you guys heard about something called autoencoder. Yeah, autoencoder is, let's say, this funny machine learning model. You throw image in, you get it out. Yeah, the whole purpose of this is get late vector, which was supposed to be a good representation of the image itself. So in philosophically, this is also self-supervised learning, but it's a very first version. Okay, and then I'm using some other data set first locally to train a so-called autoencoder. Yeah, remember, so I mean, note that here the decoder. The beauty of the decoder has the ability to transfer a vector to an image. Yeah? And then once I'm training my autoencoder, I'm just transplanting this decoder from my trained autoencoder here, and then use the whole thing to fine-tune it. Yeah? This will be my final attack model. The posterior difference, you guys just saw. Encoder structure is the one I told you, the MLP, yeah, couple of layers. And then the decoder is the one based on this, but you use the data set to further fine-tune it, and then this is the final result. Okay? To train the whole model, you use the technique we talked about in the last slides, which is how do you construct your training data set. Questions? My answer got lost everyone or before that. All right, so basically again, so the thing is I'm training the autoencoder, I only take the decoder out because the decoder has the ability to transform a vector to an image. Okay, and then I'm transplanting this here. I add it here with some pre-trained, actually you don't necessarily need to do this. You can probably even download the autoencoder from the internet. Take the decoder out. Yeah. Put it here, you add the encoder which is untrained, and then you use the data set I'm talking about from last slides. You have all the updated posterior 1, posterior n. You have the corresponding updating set. In that sense, updating set is only have one image. You use that as ground truth, you can train the whole thing to get the result.
So the coder is trained in the process as well.
The what?
The
Yes,
coder is
yeah,
in the
yeah,
process.
yes.
Okay.
But I mean, that was stuff we did in 2019, so you probably can try different settings. Maybe nowadays the decoder is so strong, you don't even need to train it. You just need to train the encoder part. Maybe also works. But it's not definitely the thing.
Yeah, my question would be like, why start with pre-trained encoder, decoder?
Why don't directly train from scratch?
Yes, why not?
Because it doesn't work well, at least like in 2019.
Okay, yeah.
Because the thing is, autoencoder train the decoder is much easier. Your image input is there.
Yes.
So here, if you train from scratch, it's like a magic. You change the number per image. Yeah,
makes sense.
Yeah.
Are your decoder weights in this posterior to image fixed when you train the encoder?
That's the same question as the asked.
Sorry, I didn't
we fine tune.
You fine tune.
We
Okay.
fine tune. But I mean, that was 2019 or 2018 we did this. But I mean, nowadays with the powerful decoder, I'm not sure. Maybe you freeze it also works.
And how do you know that the latent representation is optimal with regard to the posterior difference? Because it does not have to be.
I mean, let the training decide this. This is the whole thing of training that type of.
Right. Okay. Yeah. But
I mean, whether it's optimal or not, it depends on, let's say, the reconstruction loss. Let's say if I'm doing this pixel or L2 distance or whatever, L pips distance, it depends, of course. We don't know which is the best sense.
Yeah. Right. Okay. If you retrain it, then it's not even fine tuning. It's like just initiation of the decoder. Right?
Yes.
So you just
initiation. Yes.
1 E minus 3 learning grade, and you just start over. Okay,
yeah.
Makes sense.
Exactly. Yeah.
Are you assuming that
The trick of the lecture is you just keep on asking whether you have questions. Eventually, people will ask questions.
are you assuming that the image that really was used to the online fine tuning was in the data that you have? Because
No, we don't assume that.
you don't assume that because the posterior difference is really small. Like from my perspective,
For one sample is small. That's why we use, let's say, 100 sample. This is a posterior difference, not one sample.
are you using the 100 samples as one sample for this reconstruction?
Yes.
Okay.
Yes. Because using one sample doesn't work.
Okay.
Problem set needs to be bigger. Yeah.
Okay, thank you.
So that model gives you more information. Yeah. All right. So then that's the thing that is easier if you assume the model is only updated with one sample. Now let's do something more complicated. At least back in 2019, we think it's more complicated. Probably today as well, I guess. We assume the target model is updated with multiple samples. Yeah, let's say 100 samples. The experiment we did is maximum 100 samples. Okay, so our general principle for reconstructing this data set is the following. So our goal is to first learn the distribution of this data set. If I manage to get this distribution, from the distribution, I can keep on sampling images off, and then I do some post-processing to reconstruct data set. Yeah, but this post-processing is not really the DP style post-processing. So just like you put clustering or whatever thing. But anyway, general principle is to reconstruct this data set. We first learn the distribution. You have the distribution, you can sample from this distribution. And then you get many images, you do some grouping, clustering, and you get it. Yeah. And I think 1.5 years ago, we talked about learning a distribution. the first tool you come up in your mind is the generative evolution networks. And all is different models, diffusion models. But I mean, GAN is still hard to invent this. So again, what we did at the time is we proposed or we modified an existing GAN. So original GAN worked like the following. So anyone familiar with GAN? Everyone? I know everyone. Yeah, for the younger people, probably you don't even need to be familiar anymore because everything now is diffusion model. Yeah. So the GAN is assembled with two models. The first one is called generator. The other one is called discriminator. Discriminator is simple. Discriminator is simple. It gives you an image, and the output is a binary, real or fake. This image is real or fake. Yeah. And the so-called generator, the input is a random Gaussian noise. Yeah, 128 dimension. Let's see. You throw it in, it generates images. The goal of this is I'm letting the generator generate images as real as possible. That's the goal of the generator. I'm generating images as real as possible. And then the discriminator, the goal is to make sure that every image that's generated by the generator, I can tell is fake. So these two things are competing against each other. So I want to be as real as possible. I want, and then the other thing is I want to tell you all that's all your generated fake. You have two models. Of course, you train them simultaneously. In the end, you will converge. Once you converge, the generator itself become automatically encoded the distribution of the training data set. Yeah, because it can generate data set that looks really like the real data. So the generator itself encoded the distribution. So here's what I'm saying. What I mean by learning the distribution is not like I learn all the parameters of the distribution. It's just I'm using the generator to encode it implicitly. So I'm having this distribution, and then I give different noise, it gives me different images. Yeah, so it becomes a sampler automatically. Okay, this is the traditional GAN. So that time, to deal with our stuff, we did a so-called CVM GAN because you need to combine this with the posterior difference, which is the tech input. Yeah, posterior difference, I put it inside into the encoder. I got a latent vector. I paired together with noise. Yeah, to make sure that the whole training process, the generator has a connection with the posterior difference. Otherwise, I'm just training again. Yeah. So once I have this, I put it inside. So in my loss, I introduce the so-called best match loss. So this is a loss for the generator. So if you ignore the things in the red box, this is a classical generator loss. Yeah, your goal here is to make sure the performance discriminator loads. Okay. But once you add this, you see this, what this is means that it's actually quite simple. So for each sample in my shadow updating set, I'm letting my GAN generator to generate an X hat to be as similar as the sample in the updating set. Make sure that every sample in my updating set is learned by the GAN. Yeah, the GAN is able to learn every sample in my shadow updating set. Once you do this, then the GAN has the ability to generate, to translate the posterior difference for set of data sets. Yeah. Questions? There's a simple loss. But of course, when you train it, it's quite a, that's the time I remember there's quite a lot of tricks inside of training again. But luckily, your generation don't need to train again anymore. So the diffusion model probably is much easier to train nowadays. I think because the model is more straightforward.
Yeah. Out of curiosity, what usually can happen is that the generator learns how to fool the discriminator rather than to create real images. Did this happen to you with this setup?
Yes, because this loss is also guaranteed.
Yeah.
And also that scan, because this is generator loss.
Yeah.
Generator loss has two parts. Second part, make sure that discriminator cannot tell my image is real or fake. The first part is just to translate the posterior difference to a set of shadow updating set. Yeah. Yes. All right. right, so show some examples. I mean, that was the result back in 2019 or 2020. That time was not that good, but still, I mean, it's pretty good. So we assume that the experiments, the updating set has 100 samples. On this slide, I have 200. I have 200. Everything in the second column is the one that I reconstructed. Yeah, because I omit some details here. So once you have your GAN, your generator, you can generate an unlimited number of samples. Yeah. For example, I mean, here we also have an assumption that we assume the attacker knows how many samples the updating set has. If I have 100, then I'm letting the train again to generate, let's say, 2,000 samples. From these 2,000 samples, I do 100 clustering. K-means, I do K-means, but I do 100 means. And then I have 100 clusters. For each of the cluster, I take central sample. So the one closest to central as my reconstruct sample for that class. Yeah, for that cluster. Then I have my 100 samples. I have 100 samples, then I have my original 100 samples. I do some Hungarian algorithm to match it for display. Yeah, but Hungarian algorithm here is only for display, not for other purposes. Yeah. You see, in many cases, actually, we're not just generating what the IL4 looks like, but actually the shape or the direction. Yeah. And after that, we haven't tried further, but I'm 100% confident or 300 confident that nowadays with the current distribution models or let's say current state of the art, GAN style again 2 or 3, I guess, the result will be even better. Yeah. That's finished. Yes, okay.
So if I understood correctly, if you want to identify what were the samples, like, I don't know, a batch of 100 samples, you generate more examples and you take the closest one.
I mean, if I have 100 samples, I'm using my generator to generate 20,000 samples. And then, since I know the updated set has 100 samples, I do k-means, setting the k to equal to 100. Then I have 100 clusters of the 20,000 samples. For each cluster, I take the one closest to each cluster's centroid as my reconstruct sample for that cluster.
And how do you know that the network that generates those images actually reconstructs those samples and not only is like a good MNIST generator, and because you generate all possible MNIST, you will always.
Because I think that in the experiment we have some quantitative result. Let's say that also I think not in the paper but also offline we try that if you just have a very good MNIST generator, our performance is still better than the other things. So I don't have it. Yeah, but in the paper we have some quantitative measures. Of course, not perfect. That's the major thing of a reconstructing data set. Reconstructing data set, I think the major problem here is, let's say, how do you define the success of an attack? You know, I mean, ideally, the upper bound is, let's say, it's 2 images, the one and you reconstruct it are 100% the same, which means their L2 distance or L1 distance is 0. Yeah. But however, in reality, that will be never achieved. So you have to use some other kind of quantitative measure. Yeah. Which I don't think community has consensus yet.
Great, thank you for explaining.